Hey everyone, thanks for joining today. My name is Ben. I'm joined by Lazar on our Relations team. I'm a product marketing manager here at Sentry. And today we are going to talk about distributed tracing, what it is, and a little bit of history behind it, and how you can use it to find bugs and performance issues from your front end to your back end projects. Lazar, if you want to go to the next slide. A little housekeeping here. Not sure if everyone is familiar with the Zoom interface, but if you have a question, you can ask it right here in the chat, which is in the lower right hand of your screen. And you can also, if you have a question that you want to just get our thoughts on, you can select host and panelists, and that will go straight to us. And we also, I think a lot of people are doing this. Welcome from Nigeria, Bulgaria. Lazar, I'm located in Seattle, and Lazar, I think, is in Toronto. And
Correct.
so please, yeah, and please introduce yourself, what company you work for, maybe share what your latest TV show binge is, your new favorite movie that's out. Let's keep it casual, and please, we encourage you to ask all the questions you have. Lazar, with that, can you go to the next slide? Talk about distributed tracing, what it is, and why it is becoming more and more important with the distributed systems and microservices. And then Lazar is going to do a demo on how to use distributed tracing here at Sentry. That all is going to take about 20 minutes. And then we're going to move on to Q&A at the end. You're welcome to ask questions while we're going through the presentation. I can do my best to answer them. I am not the most technical. And so if there is anything that is framework specific, going to pass it off to Lazar at the end during the Q&A. So feel free to ask during Lazar's presentation, but there will be a dedicated 10-minute segment at the end for Q&A. With that, Lazar, please kick it off.
All right, I hope everyone's ready. Let's talk about distributed tracing. So, tracing is a really cool tool. It's a powerful technique that allows you to track the flow and timing of any requests or operation as they navigate through your system, right? As Ben mentioned, we have microservices or we have full stack applications, etc. We want to trace that. Why? We're going to see later. Because yeah, they help you understand the performance of your system and identify any bottlenecks. As you can see from the screenshot that I placed here on the slide, this is a little screenshot from the Sentry dashboard. But the traces are being visualized with something standard. It's called the flame chart. If you look on the list on the left, you're going to see a lot of operations. We have a mark, HTTP client, HTTP server. There's DB, SQL Prisma as well. Another HTTP client, a serialized span, etc. And yeah, looking at and visualizing your operational flow in this way will help you identify any performance bottlenecks and also debug weird bugs like race conditions because you can't really debug them with just a console log or a stack trace. You need to see what happened previously in order to understand what caused the issue. So that is distributed tracing. Really useful for full stack applications and microservices. And I want you all to just memorize what you see here, the whole flame chart. Because yeah, first we're going to talk about why distributed tracing exists, how we came historically speaking, how we came to this point to invent distributed tracing. We're going to do a quick demo. I have a Next.js app ready, all set up with Sentry and distributed tracing. So we're going to play around with that. And we're also at the end, in order to understand really well how it works under the hood, we're going to try to rebuild the whole concept from scratch. All right, so let's get into a little bit of history. So back in the early days, and I would say this is the 90s, we used Apache servers, and every request was being handled by a separate forked child process. So if an error happens within a certain request, we can just grab the logs, right? And this was enough. This was enough for this use case. But as you'll see throughout the time, as our libraries evolve, so does our debugging tools need to evolve. We're starting off with logs, but we're gonna see why logs aren't always the best tool. But yeah, back in the early days, this was more than enough, right? You get the logs, you see, you'll get the full picture of what happens in that process. Then we got the basic concurrency frameworks, and this is something like IIS in ASP.NET. So each of the requests that are coming from the different PCs, yeah, that's a PC circle right there. So every PC or every client sends a request to our server, and the request is being handled on a separate thread. So there's one process with multiple threads that are handling multiple requests. In order to figure out what happens, if we just grab the logs, we can't really see what's going on for that specific request, because we'll just see the logs of every request that's been, that was handled in that process. So a workaround that we needed to do is just prefix the thread name, right? This is the thread name. That request is being handled with that thread. So if you want to pull the logs to see how the operation flow went for that request, we can just filter out any of the logs or any of the messages that contain the thread name. Okay, we kind of made it work, right? Cool. It's still bearable. It's no big deal. Then we got advanced concurrency. And this is, for example, Node.js. We get a bunch of requests coming into our server, but the requests aren't really being handled in a single thread anymore. They're asynchronous, right? Node.js is an asynchronous. It's a works on futures and promises, right? On event loop. It's an event loop based framework, etc. So the request bounces from thread to thread, and we can't really prefix our messages with the thread name anymore, because we can't really keep track of the operation flow that way. We'll just receive a bunch of gibberish. What we need to do in order to make sense of the whole jungle of logs is to prefix the messages with something unique for that specific request, like an ID, right? And then we can filter based on that ID. Okay, so request comes in, we give it an ID, we prefix all of the messages for that request with its own ID, and then if we filter out based on that ID, we're good. We can still see the operation flow. But check this out. What happens after Node.js? We got distributed concurrency now. So like 10 years ago, roughly 10 years ago, like don't get my word for it, Docker and AWS showed up, and they made way for containerized services and the microservices, right? So our backends might not even, like our whole backend might not live in a same machine anymore. We are in this situation where our parts of our backend live on totally different hardware machines, but they still function like a normal backend API. So logs, in this case, I think it's hard. Like you can look at the logs for each of the microservices, but if we look at Uber's case, I think they had like 1,600 or 1,700 microservices, and one request can span to like 100 or more, or hundreds or more microservices. Figuring out what happened in that request, I don't know. That's way too. Nobody's got a time to look at hundreds of different logs. So logs suddenly don't cut it anymore, right? We need to invent something. We need to invent something better than just looking at logs all day, because even our logs are just all over the place right now, and it's hard for us to make sense of it. If you notice this, the previous slide, we had to prefix that with a unique ID for each of the requests. And that kind of paved the way for distributed tracing, right? So let's check this out. Let's see how distributed tracing works under the hood. So for example, we have, let's first solidify the concept of a trace, right? So a trace is a group of events, I would say. It has a start and a finish, right? And that trace can belong to one specific request, right? For example, update the user profile. That update can involve multiple operations spanning on multiple microservices, but it still belongs to the same trace. So this is going to be our foundation, basically. And that trace can start on the front end, for example, right? We're starting this trace on the front end. We're generating some unique ID, just like we mentioned in the Node.js slide. We're generating a unique ID for this trace, and it now lives, right? This can be the API call, or this can be the gathering the data before the API call for updating the user profile even gets executed, right? So we're starting the trace when the flow that we're trying to trace begins. And in order to make sense of how things move in our whole system, I'm not just saying backend, I'm talking about the whole system, we invent a thing called spans. So spans are going to be the smallest unit of work. This can be a function call. This can be an HTTP request. Whatever the app does at a particular moment, right? Like a logical group of operations. And whenever we create the trace, we usually create the first span immediately, and we just call that the root span, right? So those spans, for example, those spans need to mirror the structure of our code because they're like the smallest unit of work, right? So as we can call a function that calls a different function that calls a different function, so does spans can call a function, can create out of a different function and then create another one out of itself. So in order to do that, we need to keep track of what is the root span and then what is the child spans of that root span, etc. So yeah, we introduce a hierarchy in this case. We keep the trace ID and we keep the, let's say, parent ID. And we're going to wrap everything in a span context. That's going to be like a little object that lives inside of that span. And because we have the ability to measure when it started, let's also throw in a finish method to measure when it ended. So we can measure how long it took for that specific logical group of operations to execute, right? And if we visualize that, of course, put it in a Gantt chart, you see what takes too long. Like that specific span for, I don't know, sorting the array, that takes too long. And we can easily figure it out just by looking at the charts. We can identify performance bottlenecks. We can also add statuses if we wanted to. So when a span finishes, it can be like a successful finish or maybe encountered an error. We can throw in tags for each of the spans. We can throw in arbitrary metadata basically for every logical group of operations. Instead of just doing console log, we have the ability to put every piece of data that we want that describes that operation. Cool. Now we can basically get rid of logs and store all the data within the spans. But how do we take the trace from the front end to the client side? Well, there's this thing called trace ID. We mentioned that. And then there's this thing called span ID, which is the ID of the last span on the front end. We basically create a trace context that's going to keep those two values. And the front end, in order to distribute the trace, needs to send it over to the next service, whichever that is. So in most of the cases, it's going to be a HTTP header, right? We can just say, here's the trace. The value is going to be a concatenation of the trace ID and span ID. So whoever, like whatever service continues this execution flow can decide, okay, should I continue this trace or not? But we're sending it off to the next service. And that's how we can pick it up, right? And because it's just a string, we can basically move it anywhere in our backend. Here's the front end. We can move it through an HTTP header to the user service. Maybe the product service is like a cron job that picks up data from the user service produced. We can put it in a database, and then the trace can be obtained from the database and proceed to the product service can proceed to contribute to it. I don't know, hours later. And because we're talking about just a string, it doesn't matter what the piece of software is written in. We're not talking about a framework. We're not talking about JavaScript or a client side or a browser. It's a string. If you can parse a string from a database or whatever input you define, you can continue the trace, right? So our microservices don't even need to be written in the same programming language or framework. We can just grab the string, parse it, continue the trace. That's the beauty of it. And that is distributed tracing. That's how we can start the trace, build spans and introduce spans as our smallest unit of work, connect all of them as they get created out of each other, and measure the time it takes. And now if we look at this, this is called the flame chart, by the way. If we look at this flame chart and we look at the names of each of the spans, we can see what operation took place and how long it took place. So performance bottlenecks, really easy to fix. But this is not enough, right? I want to actually tell you and show you how you can implement distributed tracing with Sentry in Next.js. And we can play around with the data later on. Okay, let me switch out my slides. Here's the screen. Oh, come on, Zoom. Zoom is acting up. All right, there we go. Cool. So just move this real quick. This is a demo app that I created a little while ago. It's a flashcards app. So you basically can create your own flashcards with the question answer category. There's also the categories. It's just a basic CRUD application. And there's also a little practice section in the app where you can practice your flashcards, reveal the answer, go to the next one, etc. Cool. So I hooked up a distributed tracing on the update flashcard flow. So for example, if we grab a flashcard and update it, it's going to trigger that whole thing. And just to see what happens, I don't need to update anything. I'm just going to throw in the update. And then we can see an envelope request that sends something to Sentry. Okay, these are all the things, basically all the trace and the span and everything. But if we go back to the update, we just find it, there we go. We can see request headers. There we go. We can see a Sentry trace header that has the trace ID. Then it has the parent span ID, or like what is the span that triggered these requests. And then we have a sampled value at the end, which can be like a 0 or 1 for sampled or not sampled. We don't need to worry about that for the time being. But yeah, basically we created a span and we sent it to the backend. And now if we open Sentry, go to the performance, I'm going to reuse the React Advanced London project. It's a workshop I did yesterday just to make my life easier. I hope that's okay with you. So if we go to the updating flashcard, and you're going to see this in code as well, we're going to see all of the events. So events are just like user sessions, right? In this case, these are transactions that happened under the instances of this transaction, the updating flashcard transaction. So here are the events. This one took 1 second. So let's check it out. If we open it, we're going to see that flame chart right now. And we can zoom in and out. So I'm going to try to go back and forth these two, the dashboard and the code. So it's so you see what's going on. First we have a mark requests, and this request, sorry, span, and this span is timeless span. Basically, this is making the API request. We're initializing the API request, and then we have a mutating cache start, and in between we have the HTTP client. So let me open the code. Here's the update hook. If this is to, let me just zoom in. There we go. So this is the update hook or update method that actually gets triggered when we hit on the update button. First, we get the scope, which is automatically initialized when you install Sentry and when you're about to create a request. We create a new transaction. This is something that Sentry does. You create a transaction and then you pile everything on the transaction so it can be sent to Sentry. This is just a vehicle, basically. So we create a new transaction, updating flashcard, and then we set the transaction to the current scope. We just bind that transaction. So everything that happens is glued to that transaction, basically. Here's that first span. Transaction.startChild will create that span for us. OP means operation. So let's create a mark, just like a little flag, making the API request, and we're going to finish the request immediately, right? We're not measuring anything. We create our headers object here. And for example, if the transaction exists, and it should be existing, we append the trace to the headers so that when we make the API requests, the trace gets distributed to the backend. And let's check that out. If we open the backend now, which is the API, we're going to see, here's the put handler. We grab the scope, but then we also, instead of creating a new transaction, we're going to obtain the transaction. Because the Sentry SDK on the backend sees that there's a Sentry trace header incoming, so it's going to create that transaction for us and bind that to the incoming transaction. So everything we do will contribute, will just pile on whatever was started in the previous service or client. And this is how we can grab that ongoing trace and like put stuff on it moving on. So then we do give me the category. Then we create category checks span, and this is actually being measured. So the operation is a function. We can just give it a description. Cool. If the category doesn't exist, there we go. We set a status which is not found. and then we finish that span. We have to finish, unless if we don't finish it, it's not going to be sent to Sentry. So we have no idea what happened to that span. If the category doesn't belong, we'll just say unauthenticated. You can't really use this category. Otherwise, we'll just finish it without status, which is just okay. Then we do the same with the flashcard. Give me the flashcard. Does it exist, right? Is it valid, etc. And then we update the flashcard, and then that's it. We don't, this is basically what happens on the backend. So if you go to the dashboard, we're going to see that this is the flashcards request, and we can expand this. And we're going to see the HTTP server span that has 1, 2, 3, 4, 5, 6 child spans. First, it's finding the unique user and then finding the unique category. Then we have the category checks span. Then we're trying to find the flashcards, the flashcard based on the data. Then we do the flashcard checks. And then at the end, we do the flashcard update, which turned out to be the largest span and took the most time. It took 554 milliseconds to update, but the whole request took about 740. So yeah, so now you understand exactly which part of that request took the longest time. And then, of course, we are proceeding, mutating the cache, and I don't think there's like something specific going on, but I can show you. So if the request is okay, we already have a reference to that transaction, so we don't need to hook it up again from the server. We just need to, we can just proceed. Here's a little mark mutating the cache. We're mutating the local cache with the new data, the updated flashcard. Then we end this, we do the serialization, and then we finish. And that's basically how Sentry, how to implement Sentry in a Next.js and achieve distributed tracing. Bear in mind that we didn't even need to integrate the Sentry header. Everything happens automatically. And oh yeah, of course, if you notice that db.sql.prisma, this is something cool. This is basically an automated way to instrument all of your Prisma queries. So for example, if we go to sentry.server.config.js, and these are going to be automatically created for you when you run the Next.js wizard. If you open this one, you're going to see that there's an integrations at the bottom. And Sentry also comes in with a Prisma integration. So you give your Prisma client to the integration, and any DB request and DB query that you do is going to be automatically instrumented for you. So you're going to see how much the database queries how much time they took. So yeah, this is distributed tracing in Next.js using Sentry.